This is the next video in the chapter on chemical bonding and molecular geometry. We are going to talk about exceptions to our beloved octet rule so that you have seen them before and you know what to expect when they come up in your future chemistry discussions. So there are three main categories of exceptions. The first one is called incomplete octets. We also have expanded octets and molecules with an odd number of electrons. So we're going to start with incomplete octets. And you can guess that this means that something does not have 8 valence electrons. Specifically is when the central atom has fewer than 8 valence electrons. And usually when we see this happen, which is pretty rare, usually it is a central atom that is in group 2 or group 13. So something like beryllium or boron or aluminum are our usual culprits. So I'll show an example. So let's talk about BF3. So boron is in group 13. It has 3 valence electrons. Fluorine is in group 17. It has 7. So that's a total of 24 valence electrons. Boron is the less electronegative. Fluorine is the most electronegative atom we know. So we'll put boron in the center. Fluorine's around the outside. We'll fill in the bonding electrons, 2, 4, 6. And then we'll fill in the terminal lone pairs, 8, 10, 12, 14, 16, 18, 20, 22, 24. That's all the electrons we have available to work with. So let's check and see if we completed the octet. The fluorines have got 2, 4, 6, 8, and each of them is like that. But boron only has 2, 4, 6. Boron has an incomplete octet. And there are other ways we could try to fix this. We have tried in the past to push electron pairs from terminal atoms into the center to try to fix that. And that is another possible legal Lewis structure, but experimental evidence has shown that this bond length between boron and fluorine is too long to be a double bond, that the experimental length is closer to a single bond. So for some reason, boron is small enough that it can sometimes be detected without a complete octet. Second category of exception is odd-electron molecules. So this is a type of a molecule where one atom has an unpaired electron. And it has fewer than 8 valence electrons. So technically this is a subtype of incomplete octets in many cases. So usually this is the least electronegative atom. That's the one that ends up with the incomplete octet, except hydrogen. Because hydrogen only has 1 electron and it only needs to have 2, so you really can't take any more electrons away from that. It's like taking candy from a baby. It barely has anything to give away anyway. So these odd-electron molecules are sometimes called free radicals. And so to indicate that, we often write the molecular formula with a dot next to it to represent that odd unpaired electron that's sitting out. So if we write the Lewis structure for this guy, we have 1 carbon with 4 valence electrons and 3 hydrogens with 1 valence electron. That gives us a total of 7 to work with. We already know that there's a rule saying that carbon always goes in the center and that hydrogen is always terminal. We can put in the bonding electrons, 2, 4, 6. That's finished. The terminal atoms, so the hydrogens, don't need any more electrons because they only need 2. They only need a duet, so they're filled. So we can stick our last remaining electron on the carbon. So carbon needs to have a full octet. It only has 2, 4, 6, 7 electrons. So it has an incomplete octet in this case. And it has an unpaired electron here, making it an odd electron molecule. We can also do NO. That's a pretty common odd electron molecule that you'll see. 1 times nitrogen, which has 5, and 1 times oxygen, which has 6, gives us 11 valence electrons. We don't need to worry about which one's central and which one's terminal because there's only 2. And when we make the Lewis structure, we're going to make a double bond. 2, 4, 6, 8, 10, 11. So you can see that each of these 2 atoms has 1 set of lone pair electrons, and then oxygen has a second pair, whereas nitrogen only has a second single electron. And that's because we're going to choose the least electronegative atom as the one that's going to have the incomplete octet. So oxygen is going to have 2, 4, 6, 8, because oxygen is more electronegative than nitrogen, and nitrogen is going to have 2, 4, 6, 7, an incomplete octet. And that's because the electronegativity means that atoms in a bond are better at attracting electrons. So the oxygen's better at attracting electrons to itself. So it is going to force that nitrogen to make sure that it has 8 valence electrons, and the nitrogen will only have 7. So now the third category of octet rule exceptions is expanded octets, my personal favorite, because it's the most useful in inorganic chemistry. So in an expanded octet, the central atom can take more than 8 valence electrons. And you might wonder, if something takes more than 8, where does it put them? This only works for large elements because large elements have d and f orbitals that they can use to store those extra electrons in. So it has to be in the 3rd period or below for this to work. So it occurs for large atoms. First one that's been observed is phosphorus. I believe is number 15. Yes, so phosphorus is here in the 3rd period. So it has 3 s electrons. That subshell is filled. It has some electrons in the p orbital. And once that's filled, we also have the 3d. That 3d is empty. It hasn't been filled yet, but it's possible that those extra electrons are stored in those empty d orbitals. So we can draw examples like PCl5. So phosphorus is in row group 15. So it has 5 valence electrons. There are 5 chlorines. They each have 7. That gives us a total of 40 valence electrons. And this should feel uncomfortable. This is the first time we've ever had to try and bond one atom to more than 4 things. But chlorine can only form 1 bond. So chlorine also has to be a terminal atom. So our only choice here is to bond all 4 of these things to phosphorus and see if we have enough electrons to make it fit. So we've got 2, 4, 6, 8, 10 electrons in bonding pairs. And then we've got 3 lone pairs on each of the chlorines, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. So we've used up all of our valence electrons, and let's see if we were able to satisfy the octets of everybody. So each of the chlorines has 2, 4, 6 lone pair electrons, 8 bonding electrons. So those 5 are Good. And the phosphorus has 2, 4, 6, 8, 10. So I guess we can just make a double check. I don't really have a symbol for expanded octet. So the phosphorus expanded its octet and it put those extra electrons somewhere else to be able to bond to all 5 of those chlorines. And we only say this is true because we have experimental evidence showing that it is so. Let's do one more. Let's do something where we could possibly bond to everything without expanding our octet. So we've got sulfur and oxygen are all in group 16. So that's 5 atoms with 6 valence electrons plus 2 from that negative charge is going to be 32 valence electrons. Oxygen is above sulfur in group 16. So oxygen is going to be the more electronegative. So it's going to be the terminal one. So we'll put the sulfur in the center and the oxygens around the outside. So we can put 2, 4, 6, 8 electrons here, and we can fill the terminal oxygen atoms octet, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. And we won't forget that 2 negative charge over here. So those are filled. We can check the octet, 2, 4, 6, 8 for oxygen, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, and for sulfur, 2, 4, 6, 8. So technically we can draw a legal version of the structure without expanding the octet of sulfur, but we can check the formal charges to see how stable this molecule might be. So each of these oxygens has 6 minus 2, 4, 6, 7. Formal charge of -1 for each of those. And each of the sulfurs has 6 minus 1, 2, 3, 4 is going to give us a +2. And +2 is a rather large formal charge, and we would really like to see a smaller formal charge for that so we can feel that the molecule is more stable. So another way we can draw the molecule is expand the sulfur octet to try and lower its formal charge. So we will take 1 lone pair from 2 of the different electrons and push them in to make 2 double bonds across from each other, leaving 2 lone pairs on each of these and 3 lone pairs on each of these. Okay, octet check, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. And for sulfur, 2, 4, 6, 8, 10, 12. We are way, way expanded, which seems really unfavorable, but let's check the formal charges. So the oxygens are 6 minus 2, 4, 5, 6, formal charge of 0 for these 2 double bonded oxygens. The singly bonded ones are 6 minus 2, 4, 6, 7, formal charges of -1. And for the sulfur, 6 minus 1, 2, 3, 4, 5, 6 bonds, formal charge of 0. So the reason that we predict that sulfur expands its octet by so much, all the way to 12, is because the formal charges in this molecule are much lower and more stable, as opposed to this first one, which had complete octets for all the atoms, but had very high unfavorable formal charges. So we expand the octets in our model to help account for more reasonable looking formal charges. So that is everything that you need to know about Lewis symbols and Lewis structures, and a couple of cases that don't quite fit into the rule. So let's go ahead and cross off Lewis structure on our atoms first graphic. There we are. So we've now learned about bonding types, nomenclature, and Lewis structures under molecules. We'll move on to geometry and shape next.